So in this video, we are going to discuss the idea of a reaction quotient, which is going to be based largely on trying to determine if a reaction is at equilibrium or not. Very similar to number 6 from the stations that we talked about in class yesterday. So let's say you have this reaction here. Hydrogen plus iodine gas is in equilibrium with hydroiodic gas, HI. And this says this reaction occurs in a flask, and at some time, the concentration of H2 is 0.001 molar, concentration of I2 is 0.002 molar, the concentration of HI is 0.0187 molar. If K equals 51, are we at equilibrium? So in order to figure out that, we need to set up the equilibrium expression. So first thing we need to do, always with equilibrium problems, write the expression. So K equals, and let's write our values without plugging in numbers. So since these are concentrations in molarities, I'm going to use brackets, not partial pressures. So HI squared over the concentration of I2 times the concentration of H2. That's what I'm going to set up first. Now to figure out if I'm at equilibrium, I need to solve for what K is. So I'm going to go ahead and plug in my numbers. So for HI, we were given that the concentration was 0.0187. So I'll plug in 0.0187. That's going to get squared. For I2, it's 0.002. And for, let's use green here, H2, it's 0.001. So that would be my setup. If I go ahead and do all the math and I multiply everything out, I get a value of 1.748. Okay, so now we need to compare. It's telling us if K is equal to 51, are we at equilibrium? Well, when we plugged in these concentrations, we get a value of 1.78. So no, not at equilibrium, because the value that we got for K is not what K should be. So what does that mean? It doesn't mean that this number 51 is wrong. It just means that at these concentrations that are given in the problem, they're not the equilibrium concentrations. So this reaction is going to need to change. It's going to need to shift one way or another in order to get to equilibrium. So conceptually, what you need to think about. Right now, the reaction is just at 1.748. That number is much less than 51. So in order for this number to get to 51, this value has to get bigger. And for this value to get bigger, let's think about what that represents. It's products over reactants, essentially. So in order for this value to get bigger, the amount of products is going to have to increase. Another way of saying that is the reaction is going to need to shift to the right. Okay? One thing that we need to recognize, and we're going to summarize that in a second, is whenever you're solving for K at any time, any conditions, what you're really solving for, the other variable that we use to represent that, is actually Q. And Q is what's called the reaction quotient. The reaction quotient. It's basically a value that represents the state of the reaction, which could be at equilibrium or might not be. We only use the letter K if we are at equilibrium for sure. Otherwise, we use the letter Q. Okay? And we'll do another example problem of that in a second, but first I want to summarize this idea of how the reaction will shift. So, if Q is less than K, so for example in the problem before, Q was 748, excuse me, and K was 51. So if Q is less than K, then that means that then the reaction will shift right. What that means is that we're going to make more products. So in general, if we have some reaction of A equilibrium with B, if when we calculate Q, that value is less than what K is, the reaction needs to shift to the right. Some of A needs to get turned into B to get closer to the value of K. On the other hand, if the value of K is less than Q, or another way of saying that is Q is greater than K, then the reaction will shift, will shift to the left. Because in order for us to, if Q is bigger than K, that means the value of the products is over reactants is too large. This is too big. So to make it smaller, we have to turn some of it into reactants, which means the reaction is going to shift to the left. Another way of saying that is we are going to make more reactants. And finally, if you solve for Q and you find out that Q is equal to K, then what does that mean? Then that means we're at equilibrium. The concentrations of each compound, equilibrium, are what they need to be for the reaction to be at equilibrium. So these are the three main conceptual things that you need to know. How to compare Q and K to each other. Let's do another problem where we actually solve for Q and then apply this again. So, for the reaction above, K equals 0.338. So they give us the equilibrium constant already. If the partial pressure of SO3 is 0.16, partial pressure of SO2 is 0.14, and O2 is 2.5, these are all in ATM, then to write that in the problem. Which way will this reaction shift? Okay, so we need to predict a shift numerically. So this is not Le Chatelier's principle quite yet conceptually. It is with numbers. So first thing, we need to figure out the state of the reaction. We need to solve for the reaction quotient, Q. So always, always, always write the equation first. So this is going to be the partial pressure, since I'm given pressures. Partial pressure of SO2 squared times the partial pressure of O2 divided by the partial pressure of SO3 squared. So now let's plug in the values. Again, these pressures, we might be at equilibrium, we might not be. So SO3, we'll plug that in the denominator. So 0.16 squared. We're also given SO2. So we'll plug that in on the numerator and square it. So 0.41 squared. And we're also given the partial pressure of oxygen, 2.5, so times 2.5. So that would be the setup. If we go ahead and solve for this mathematically, what we get for a final answer, don't forget your order of operations. You have to square this first, square this also, before these get multiplied, and then before you do the division. You get a value of 16.416. So this is the state of the reaction right now. We're given that K is equal to 0.338. So K is equal to 0.338, and Q is equal to 16.416. I'm not worrying about sig figs yet because I'm just trying to predict a shift. So what do we have? We have that Q is clearly much greater than K. That means that I have way too many products. The pressure of my products is much larger than it needs to be at equilibrium. So what's going to happen? A bunch of these products, okay, which I'll highlight here in yellow, these products are going to need to get turned back into reactants in order to make the value of K get small. So if they're getting turned back into reactants, excuse me, boom. This reaction is shifting to the left. So reaction will shift left since Q is greater than K. That's the big idea. You need to be able to calculate a reaction quotient Q. Same thing as what we did earlier with equilibrium expressions K. And now what we need to be able to do is predict shifts by comparing Q and K. So using these three summary points together.